Good morning, everyone. Thank you very much, Eduardo, for this introduction, where you invite us to see what we have today that will be incredibly interesting. We will start this first part of today's seminar with Krystyna Pechena. And as you mentioned, she collaborated with the working group on cybersecurity. And it's been a great support. Thank you very much for her work. She's an expert in advanced econometry with big data analysis and big data. She is a graduate of the University of Oviedo in business administration. She is leading currently Kape-R company, analyzing advanced mathematical models, and she's collaborating actively with the Asturian Principate government. Krystyna, if you can share your screen now, your presentation, you can ask questions on the chat box. They can be answered after the presentations or in a Q&A part whenever all the presentations finish. Thank you. First of all, thank you for the opportunity to be here and share with you our experience related to big data with regards to smart grid. To start, I'll just give a small introduction on big data and distribution networks, and then we'll see the applicability and potential of the mathematical models and advanced analysis of big data, showing concrete examples that we've been developing in European networks. The big amount of information that we have in our society, like in social administration, internet, and social networks, or internal data that are available for companies, is a great opportunity that allow us to improve efficiency in processes. For instance, to avoid bottlenecks, to pay attention to demand, to know the determinants of issues and the impact, to be fast decision making, to track in real time and have automated processes to improve services and adapt the needs of the customers, and also to have discoveries and develop new products, for instance, a treatment for a disease. A really relevant point is that within the years, data storage costs have been reduced. We have a lot of advanced technology that allow us to store and manage. And the amount of data that we have available in several countries provides an opportunity to look solutions for high impact problems. To illustrate the possibilities that we have with all this data that we have, I have a lot of examples that we have to measure the impact that they can have smart grids on society. The first example that I would like to share, it's a model related to the predictive maintenance for grids, distribution networks, for neutral, to predict outage and other issues on smart grids. This model is a tool that allows us to get damage on neutral losses, and these are the problems that we have in low tension or low voltage networks. Within the last years, allow us to detect defects that are going to have losses in the neutral, and to allow us to have enough time, that can be days, weeks, or years to correct before having the issue itself. The images that we can see in here is the effect that they can have. There is a neutral cable that is not well connected, lost, and it started to burn, but it hasn't produced a bigger problem in the installation of the customer. Whenever we start to apply these algorithms at the beginning, in the field analysis, they wanted to check the analysis from one point of the cable whenever it's lost, and within the time to measure the problem that they will have, and then correct the effect before the problem happens or takes place. In this example of a neutral cable that was getting loose, the unit measured with a thermal camera to confirm that that point was heating up. We have historical data to check how the defects will produce losses, and the results sometimes are months or years. Whenever there are, or for instance, whenever a truck passes by and they get the neutral cable, but there is not way to predict that yet. With all this and based on experience, we've seen that the model allows us to have enough time to check on site the defect before the failure, the consequence happens. And where we've applied this algorithm, all defects that have been detected and improved, they haven't caused any failure on the neutral cable. And this help us to be precise on the geolocalization of the defect in the network on the grid very high, reducing the exact point in the grid on the low voltage grid to help the groups to localize the defect quickly. And by applying this model has allowed us to extract a lot of learning of the causes that have been detecting defects. And the causes could be the weather, and you can classify the different types of defects depending on different materials and other aspects. This model is being implemented in several distributors and in the areas that they've been applied for a while, and where they've been checking all the possible neutral defects, all the failures on loss of neutral power or have been avoided, fires avoided, where operators have been taking really seriously how to prevent issues. The benefits that are more important here for the predictive maintenance are a safer grid for customers, avoiding material and human losses, and for the distributor, the costs for compensation costs have been reduced as well. So using the data from smart grids have the potential, and the potential of the data show the balance of the low voltage to detect direct links. So this allows us to, the direct coupling analysis allow us to determine the cause of the measure of mistakes. For instance, sometimes some low voltage equipments were not measured correctly to check which are the technical issues or non-technical issues, and they allow us to see the losses and reduce the low tension losses for over 50%. In this slide, you can see two attempts to connect illegally And what we've witnessed with this logarithm is that it can help the funds of the European Union. In this model, you can understand the reference values of the losses for consumers connected to the low voltage network grid in Spain. Based on the information from 2019, we estimate that from whenever the energy is generated to the customers, there is a 60.4 loss of energy, or 9.2 before going to the low voltage grids. So there is loss in substations and transformation, low voltage centers, and 7.2 in this area. So in the transformation centers from low voltage to middle voltage, you can see in this network or grid that there are losses within this 7.2 of losses in the low voltage grid is due to technical losses depending on the charges, the resistance of the cables, temperature, and other are due to non-technical aspects and frauds. There are over 200 programs of a lot of complexities to integrate geolocalizations where the losses and non-technical losses are within the network. This slide reflects the losses in Spain to provide the final consumers depending on the voltage area where they are connected to. As you see in the chart to the left, far right, only 46% of the total consumption in Spain. Losses for these consumers are 74% of the losses in the whole grid, as you see in the chart in the middle. And the difference is because of the fraud that they have in this part of the grid. We estimate that 20% of the losses in the whole grid in Spain is 20% of the fraud that is caused in the middle chart. And this fraud is more than half of the losses in the low tension grid. To have a more concrete information, you can measure the impact with public data available and where this model is applicable in Spain in 2019 and focus on the losses only in the low tension grid. As I mentioned, over half of the losses in the low tension grid are non-technical, that is frauds, and taking into account the price, the average price in this area in Spain, the payment, the cost, it's 882 million of euros per year, through 794 millions of euros per year for direct illegal connections. And the three-phase counters with illegal connections have 26 million euros per year. And with this algorithm, we can detect all the types of frauds to be able to understand the losses in the low voltage losses. And the non-technical losses are over 50%. Based on the results of the application of this model developed in the distributor grid, we can ensure that the model can have a close to 100% precision when detecting the frauds. And this is related to smart grids. And to understand what this data allow us, I want to give you a brief summary of the model. but it has over 200 programs that are highly complex. In the following pyramid from the bottom down, you can see the summary. So you have, well, in the base of the pyramid, you see a balance of the gross information, and we have the transformation information. The result that we have with this balance is a precise information of the 6%. For this reason, if we see this, we don't detect the frauds and reduce the losses.
In the transformation centers, we may have 4% losses when actually they have 90% losses. Once realized balance with the data, with the gross data, we increase the level to implement algorithms that allow us to detect all the measurement errors from the different events. Once those errors are detected, they are classified and segmented as for each kind of error of measurement. We estimate the actual measurement that should have been read. After these estimations, we automate and we program an algorithm that corrects all kind of measurement mistakes without ever over projections. Besides, with all these steps and algorithms implemented, we are capable of knowing the cause that originates each kind of measurement error, which since maneuvers and the grid may generate measurement or reading errors in the different equipment. Besides these corrections, others proper from the developed model are applied and that allows us to obtain the low voltage aggregate balance with a higher than 99.75% accuracy compared to the 6% of the starting balance we obtain with the gross data. After this, we see for connection errors with other stock errors, and we allocate an estimation. Then this way, we correct most of the inventory errors and associations. Once amended, are having an accuracy of 100%, which are technical losses which are normal from the transformation centers of the grid in each period. Finally, after knowing the normal technical losses, we can differentiate which losses are very high to review. Um, Regarding the results of the accuracy we're obtaining with the model, as I said, is where we find relevant fraud or errors of association of connection inventory, which are very difficult to amend, to correct. Regarding economic data from the project, we are having a cost of field review of about 29 cents of euro per megawatt recovered, and the annual benefit taking into account the average price per megawatt in low voltage in Spain, it would be 152.8 euros per megawatt of reduction of losses. Having into account that the fraud losses are reduced as a mean in 10 years, the benefit for 10 years is 1,528 euros per megawatt a year. In 10 years, the highest volume of the fraud we have obtained is direct fraud. A small portion is bridges of the jumpers of triphasic counters have higher weight than the monophasic jumpers. Main benefits for society are, on the one hand, reduction of the price of those given the cost of the energy defrauded at the end of the day are assumed by consumers, and therefore by the society, making the bill more expensive both for domestic consumers as well as for companies that lost competitivity and for the state. And on the other hand, we will have a safer grid given connections lead to uh, less losses. In the next slide, I've included other lines. As we can see, it could be applied having the data from the smart grids. Within the predictive maintenance, another impact model to have a more secure and reliable grid is in the little model to detect the mid-voltage lines that are having vegetation in order to avoid losses or avoid failures due to this reason. In terms of asset improvement, another use case using data from smart grids are, for instance, a model determining the phase each meter is connected to. Knowing the phase is connected each meter beside other advantages allows to make a layer balance to reduce technical losses and know in further detail the grid, which allow things such as knowing which meters could drop if we cut full phase. Another example would be a model to detect failed equipment in order to fix them or substitute them. There are other more simple ways of detecting other less significant kind of fraud using artificial intelligence technique, event combination, and changes in consumption patterns. In summary, and to wrap up, uh, the information by uh, smart it allows to develop, among others, solutions to avoid problems in the grid, reduce losses, same as well as giving better service to final consumers at a lower price, among other examples and applications, becoming the grid into a smart grid. Regarding the quality of the equipment installed in the smart grids, it's very relevant that they gather a wide range of variables as those measurements of the variables to be reliable. We've seen many cases of companies because they, in order to save a little bit, they have installed less reliable equipment, and at the end of the day, it's more expensive to them. With this, I want to finish my presentation, but I want to also thank the invitation to this forum. And of course, I am at disposition of everyone in case of any question or comment. Thank you very much.
Muchas gracias, Cristina. Excelente
Thank you,
presentación.
Krystyna. Excellent presentation and very interesting to see all the applications you showed, the number of things that could be made. In this moment, we don't have any question. Oh, yeah, there is one question. Hello, is there any experience of that solution with Chile? No, with Chile, because these applications are applications with smart meters and other smart grid devices. What I wanted to show, I could show with the slides, is the potential these data have issued or generated by the different equipment across the smart grids. If there were a smart grid deployed in Chile, we could apply any of these developments. Okay, perfect, Krystyna. Thank you very much.